So let's go ahead and go through these solutions for the C1 reflection assignment. Basically, we're looking at locations and distributions. So this starts with a cumulative plot, and you can see here age of employees. Let me get my pointer. You can see age. There you go. Which becomes bigger. Your options. Your options is just so on the bottom axis here, you can see age of employees. And here you see cumulative frequency on the vertical axis. So pay attention to that. And it says, given this cumulative plot and using the most commonly accepted definition of outliers, what ages would be considered outliers? So this is kind of a tricky question. And it actually is going back to our previous information in Chapter 1 with definitions of outliers. We're going to need IQR. And so we're going to have to remember what the definition of IQR is. Finding a median on the graph like this didn't make sense. Here's the good news. You don't need the median for this calculation because the median is a little tricky on there. It looks like it's about 43, 44. But the good news is we can find IQR because Q1 and Q3 are very easily visible. So first of all, Q1 is at the 25% mark. So looking horizontally, where does the line intersect with the 0.25? It's at 40, all right? And then Q3, where does it hit 0.75? It's at 50. So let me see if I can find this. It doesn't give me a chance to here. I'll just do it this way. This is a little easier. So here is, there we go. There's the 25% mark, and there's the 75% mark right there. Okay. So there's, oh, yeah, there's your Q1 and there's your Q3. So IQR is the difference of those two, which is 10. And then the unusually low, we take Q1 minus 1.5 IQRs. 1.5 IQRs is pretty simple. It's 15. And we take the 40 minus 15, which is 25. Do we have any data points below 25? Yes, we do. We do. All these data points over here. Actually, sorry, not all those data points over there. Let me change colors. For your options, sorry. All of these points, we'll do it with red. Right here are the potential outliers. We can go ahead and double check for unusually high. So we're going to take, well, I don't have to do it because it's the only option that works between 20 and 25. I could have done unusually high, adding 15 to 50, and I would get 65. And as you can see, this stops right here at 60, so we never get to this 65 spot. So no outliers up there. So 100% of our data, the way to look at these, is from 20 to 60. 25% of our data is from 20 to 40. Another 50% of our data, that middle box, is from 40 to 60. And then the last 25% of data is from 50 to 60. So that was a 50 there, not a 60. Okay. Question 2. If 10 executives have salaries of $80,000, 6 have salaries at $75,000, and 3 have salaries at $70,000, what is the median salary? So I could list these all out. Honestly, I could pump them all into a Statlet or to a calculator and have it tell me the median. But I don't feel like putting in $80,000 10 times and $75,000 6 times and $70,000 3 times. So I'm just going to say, how many total data points are there? So if basically it looks like there are 19 data points. All right, this might go a little out of order, sorry. So the midpoint is going to be at that 19 divided by 2, which is 9.5, or between points 9 and 10. If we list ascending, and it shouldn't matter if I go ascending or descending, it'll work the same either way. 0.9 is 75,000, and 0.10 is 80,000. So the midpoint is halfway between right? So first of all, there's my ending data points. The midpoint's halfway between, which is 77,500. And there is your answer for number 2. 3 and 4. So the dot plot represents the number of AP courses that 26 seniors had taken in high school. All right, and then one of you commented, well, one of your predecessors commented, I need to work on percentiles like in question 4, where it asks what percentile specific dot falls into. So the important thing about percentiles is that you got to remember it's a percent at or below. All right. Sometimes it says percent below. There are 2 definitions of percentile, which is super annoying. And AP teachers gripe about this on Facebook. But let me put it this way. When it comes down to it, you're fine either way, whichever method. So first of all, it asks, what is the median number of AP courses taken by these students? So there are 26 seniors. So I need, basically, we have 26 seniors. Oh, someone asked about percentile, so I think I'm just doing 4, but I'll cover the median as well. So there are 16 dots at 4 or below. All right, so tell you what, before I do that, let me do my median. So there are 26 seniors, so it's going to be at the 13th data point. So we've got 1, 2, actually between the 13th and 14th. You add 4 here, you get 6. And in fact, I happen to know this adds up to 16, right? Because we had 16 seniors. That's what I said here. So between the 13th and 14th. So let's count these up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So the 13th and 14th are both in this middle pile, right? The 13th and 14th are both in that middle pile somewhere, which means my median is in there. So that would tell you the answer for the median should be 3. All right, the answer for the median is 3. Now let's say, what percentile is someone who completed 4 AP courses? So we look at or below. There's 16 data points in this box. And so we're just going to basically take 16 out of 26, which is 69.692. or 69.2%, also known as, whoops, let me come back, also known as the 69.2th percentile. On to question 5. Data were collected on amount of minutes spent on the quiz. Here's the 5-number summary. So you got 6, 15, 17, 20, 30. Now, I prefer you label your 5-number summary when you give it to me. But if it's listed in order and they can give it to you like that, you should know what all 5 of those numbers are. Min, Q1, median, Q3, and max. Which of the following are not true for this statement? Which of the following statements probably should say is, because we only have one answer, ignore that, is not true for this data. Less than half the students spent more than 15 minutes on the quiz. So we know our median is 17. We don't know that less than half did. All right, so actually, let me go ahead. I'm getting ahead of myself. In Unit A, the 5-number summary represented a box plot. It listed whisker numbers as outliers. Why are they considered outliers when they weren't for box plots? I don't understand why ST minus mean equals ST. So let's go ahead and continue on to fix it, solving the problem. So we know that A is not true. 15 is at Q1. So we know more than half is greater than 15, right? Or at least 15. So we know that 50% of kids got 17 or higher, 50% got 17 or lower. So we know that at least half spent more than 15 minutes, right? So we know that's not true. B could be true. 75% of students spent between 15 and 30 minutes. It's possible, all right? The max is 30 and Q1 is 15. 75% of data is between 15 and 30. However, there could be some data below 15 as well that, so it could be actually more than 75. So for example, you could have some 15s that are in this tiny section here between the min and Q1. So we don't know. C is true. IQR is 20 minus 15, which is 5, the upper bound. we take Q3, which is 20, and that should say plus, yes, plus 1.5 times 5 is 27.5. So we know that 30 minutes is an outlier. So this is definitely an outlier. Pretend that doesn't look too good, does it? I should change it to yellow. All right, and then let's look at D. D is the lower boundary, and we take Q1. Let's see. Do I have Q1? That's the wrong number, isn't it? Give me a second. Oh, I fixed it here. That's the IQI. That's fine. 15 minus 1.5 times 5 equals 7.5. And 6 is definitely below 7.5, so we definitely have an outlier there. All right. The student who took the quiz in 7.5 minutes is in the 25th percentile. Have no idea, because it looks like the 25th percentile is actually 15. Who took the quiz in 7.5 minutes. Let's double check. Not fond of the wording on this one. Yes, I think this is true because it says in the 25th percentile, but not exactly at the 25th percentile. So this makes me go, I do not like the wording on that one. You won't have anything that mean. So I would say the answer is A, because we know for sure that this is not true. Okay, answer is A. So I can understand if you got a little confusing because of this meanie option right here. Okay, they said in the 25th percentile. They didn't say they were at the 25th percentile. Okay, question 6. So it is estimated that 20% of all drivers do not signal when changing lanes. In a random sample of 4 drivers, what is the probability that at least one doesn't signal when changing lanes? So this is sort of like a double negative. And I've got some orders, so let me get my orders caught up. There we go. And I'll walk you through it. So we've got 4 drivers, right? There's 4 drivers right there. What is the probability at least one doesn't signal? So we have 0 doesn't signal, 1 doesn't signal, 2, 3, or 4 doesn't signal. It's easier to calculate the complement. So we're looking for the probability of this occurring, right? Well, I could calculate all 4 of those. Some of these are actually tricky. I haven't taught you how to calculate some of these in here. Or, well, technically I have. You could do a tree. But if you have 4 drivers, that's 2 to the 4th. That's 16 branches. You don't want to do that. So the complement is easier because I could just calculate that 0 don't signal. And so 0 don't signal, which is really tough because that's a double negative. So that basically is everyone signals. So that's the complement. And so I wrote it as probability of they signal, 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 which is 0 not signaling. That's 0.8. Where did I get 0.8? Well, the probability they don't signal is 20%, right? That's do not signal. But these are people that signal. So 1 minus 0.2 is 0.8. So pay close attention to that. And so it's 0.8 to the 4th. Since this is the complement, I just go 1 minus that probability, or 1 minus 0.8 to the 4th, which is choice B. On to number 7. Suppose you toss a fair coin and it comes up heads every time. Which of the following is a true statement? By the law of large numbers, the next toss is more likely to be tails than others. No, oh shoot, don't tell me. I'm going to go through these again. All right, so law of large numbers does not predict individual outcomes, and your next toss is sort of like an individual outcome. It means on average, your actual will approach your theoretical proportions, okay? Then it says, by the properties of conditional probability, the next toss is more likely to be heads up, given that 10 tosses in a row have been heads. Previous tosses do not affect next tosses. And that also rules out C, because coins don't have memories. And the law of large numbers tells how many losses will be necessary. No. It just shows long-term averages, not actual specific predictions. So we say none of these statements are true. And I know it's always hard when none of them are true. That's a tough one. Okay, so just ignore that. Oh, yeah, I saw the broken scale there. So, starting over again. Consider this picture of revenue over 3 years. Which of the following is a true statement? And I struggled with question 9. It seemed to me that there was more than one correct answer because I failed to really read the values instead of looked at the height of the bar scales to compare them. I wouldn't say it's a horrible move. It's kind of understandable. So I can understand how you got stuck on this one. So I'm okay with it. So I want to go ahead and get a highlighter. And there we go. And an interesting thing, because they pointed out here, they didn't look at the height of the scale. So you can see this actually has a broken scale where I marked it in red. So let's go ahead and work through this problem. I'm just going to go through each of the answer choices. So choice A, revenue dropped approximately in half from 2011 to 2012, then half again in 2012 to 2013. Again, because of the broken scale right here, it looks like it dropped in half, but that's not starting at 0. So let's look at actual values. So 110 to just 100,000 is not dropping by half. That's false. Then the next one says revenue was greater in 2011 the next 2 years combined. That is also false. All I did is I eyeballed, added up. You got 110 versus 100 plus 95 is definitely greater than 110. So that's false. C, revenue in 2012 was approximately 2/7. So let me look at that. 2/7. This is a little closer to 1/3, I would say, than 2/7, because what I did is I took the total revenue and I added it up. I got 305. Then I took the revenue in 2012, which was 100 divided, and I'm getting about 1/3. So I'm going to say no, not quite. Not quite. Then let's say 2018 revenue was 1/7, which is more like 14%. And if I take the revenue in 95, which was 2013, which was 95,000, and divide by 305, I get 19 divided by 61, which is also false. The real thing is, this is not a histogram. Histograms here, we have frequency, usually on bar height. So bar height should correspond to either an absolute or a relative frequency. These are revenues. So this is actually more like, I don't know, a time series or something weird like that, maybe even a bar graph. It's hard to say because 2011, well, you could argue whether those are quantitative or not, and it depends what you're doing. It's not a histogram. Histograms give us values on this horizontal direction for the bars, so we know how the bins fall. If you look at the previous examples, this is not a histogram. Okay, on to question 9. Question 9, at the Census Bureau website, you can view detailed data collected by the American Community Survey. The following table includes data for 10 people chosen at random for more than 1 million people in households contacted by the survey. School gives the highest level of education completed. So who are the individuals? Well, they surveyed 10 people. So these are the people they gathered data from. Those 10 people are the individuals. So make sure you can understand when we talk about individual, it's the subject which you record data for. You can see the individual has a weight. Someone's pretty lightweight here at 91 pounds. And then we got some heavier people. Ooh, that one's heavier, right? And then you have their age and travel to work, how far they go, right? So there you go. Here is a pie chart prepared by the Census Bureau to show the origin of more than 50 million Hispanics in the U.S. in 2010. Approximately what percent of Hispanics are Mexican? And they also want to know Puerto Rican. So first thing that you can notice is us Mexicans. Well, technically I'm not Mexican. I'm Hispanic with Mexican origin. So, I counted that. My mother's from Mexico. So anyways, we take up greater than 50%, yes, but we're not quite 75%, okay? So we're pretty sure that any values, our actual values somewhere from 50 to 75, but it's not as low as 50 because we're more than half, and we're not quite 3/4. So I'm going to cross off anything that doesn't fall in that range. So 50% we know is too low, 9% definitely too low. 63% is fine, 75% is too high. So I've really eliminated it down here. Then the other thing is, it's not impossible. I can roughly estimate percents. Pie graphs are fantastic for that because we're very good. We can do our quarters and our 25%. So the correct answer is D. The correct answer is D for number 10. Students in a high school stats class are given data about the main method of transportation to school for a group of 30 students. They produce the pictograph shown. Anytime you see pictograph, beware, pictograph bad. Usually, almost always, pictograph bad. You can have a good one, but they're hard to make. All right, which statement correctly explains how this graph is misleading? Each student each picture should only represent one student. They do, well, actually, I apparently skipped a few. Not required to have one picture per individual, all right? Part B, the school buses should be much longer than the cars. Even if the buses were scaled better, so you could say, oh, the bus should be 3.5 cars, because that's how many people it represents, right? And it definitely doesn't. So there are other issues as well. That's not the only issue. The graph is missing a scale on the horizontal axis. The pictograms actually kind of tell you a scale in the sense they give you a key, right? You got a key right there. And there's nothing wrong with being colorful and eye-catching. The main problem with pictographs is that the area of the picture, so not just length, but area, should correspond to the area that you're trying to represent. So here you got 2 bus walkers, and you can see 3 bus walkers here. It's the same as that. So, and the areas are also, maybe this should be, yeah, it's, I kind of like the same size images. If they had done something where these were all the same size and used more similar units, this probably would have been better, but it's very easy to mess up a pictograph, so be careful. Did I call it a pictogram? Yeah, it's a pictogram, same idea. All right. So the issue with pictograms or pictographs is that the area must be proportional to the units. They are not proportional here. Number 12, how old is the oldest person you know? This is an actual, I've seen this chart before. Prudential Insurance Company asked 400 people to place a blue sticker on a huge wall next to the age of the oldest person they've ever known. So you can see it got kind of lumpy there. So let me go ahead and draw a rough sketch of what the shape looks like. It's not perfect. So, describe the shape and distribution. Definitely left skewed. So that makes my life easier because I'm going to cross out anything that is not left skewed, like symmetric, right skewed, right skewed. And then it says, oh, the shape cannot be determined because data is categorical. Pretty sure data is quantitative, not categorical, so cross that puppy out. And then we have left skewed with a single peak between 90 and 100. So again, remember you want a very rough shape. I could tell they were trying to go higher right here, right? Because they were running out of space. And so I tried to make that peak higher, so your true peak is in this area. On to problems 13 and 14. Do adolescent girls eat fruit? We all know that fruit is good for us. Here's a histogram of servings of fruit per day claimed by 74 17-year-old girls in a study in Pennsylvania. What is the median number of fruit servings per day? So we need to know the total data points, and we said there's 74. So I'm going to go ahead and number. All right, so you see it. Notice I put some numbers on the bars. 74 divided by 2 is 37. So since I have 2 sets of 37, my median is between points 37 and 38. And I'm just putting the titles here on the bars here. So I know 15 data points are here, and then you're going, wait, but that's not 26 data points. That's not what I'm trying to represent. I'm trying to find points 37 and 38. So if I start in bar 1, I get 15 data points, and I get 26, and then I get up to 41. So both data points are in this bar, all right? So the median is in the third bin, right? And under 2 servings of fruit, all right? So the third bin represents what value? The third bin represents 2 servings of fruit. Now we're actually assuming that this is pretty straightforward graph because we're assuming you're not having half a serving of fruit, or so we're assuming these are actually integers, right? So we can say the median is 2. So everyone in here ate 2 servings of fruit. Here they ate 1 serving. I'm sorry. Everyone in there ate 3 servings of that. Yeah, 2 servings of fruit. These people ate no servings of fruit. No wonder I got confused. And then these people ate 1 serving of fruit. I love my fruit. So good. All right. What is a mean number of servings of fruit per day? Now, some of you are like, oh, I can make those numbers out. I'll just put them all in Staplet or my calculator and let it spit it out. And you can. But if you want to save a little time, you know the mean is greater than the median. So it is not, here, let me go ahead to a different color. Color not quite. So we know that it is not these guys, right? This 0, 1, or 2, right? So it's not these. It's greater than the median. Okay, so my choices are 2.62 and 4 servings per fruit. Now, a mean, 4 servings seems too high. The mean should sort of be a balancing point if I were trying to balance it under here. And I think it's a little higher than 2. Don't think it's all the way to 3, but it could be in there. But 4 definitely, it would tilt. So I will say the answer is 2.62 servings per day because 4 seems just a touch high. Okay, a media report claims that 50% of U.S. teens with smartphones feel addicted to their devices. Huh, I would have thought it was higher. A skeptical researcher believes that this figure is too high. Oh, I disagree with the skeptical researcher. Okay. No bias here. She decides to test the claim by taking a random sample of 100 U.S. teens who have smartphones. Only 40 of the teens in the sample feel addicted to their devices. Does the result give convincing evidence that the media's report claim of 50% is too high? To find out, we want to perform a simulation to estimate the probability of getting 40 or fewer teens who feel addicted to their devices in a random sample size of 100 from a very large population of teens with smartphones, in which 50% feel addicted to their devices. Now, there's some other issues with this study here, which we'll address in future units, like they asked them, what did they say? They said only 40 of the teens in the sample feel addicted to their devices. And, well, actually, this does say feel addicted, so I guess it's fine. I guess it's fine. All right. So if they feel addicted, okay, I'll set aside my reservations. So what we're trying to model is 50% outcomes, right? This is what we're trying to do. And we're trying to see if we can get 40 or fewer teens who feel addicted to their devices, all right, out of 100. So their simulation plan is let 1 equals feels addicted and 2 doesn't feel addicted. Initially, I'm like, what? Wait, only 2 outcomes? Well, if you have a nice random number generator and you produce 100 random integers from 1 to 2 only, that's fine because you have exactly 2 outcomes. If you were using a random number table, remember each digit would be 0 to 9, so it could represent, you take half of those 10 outcomes and say, oh, feels addicted and half doesn't. So we'll talk about that in some of the other answer choices. Repeat this process many, many times. So it does say many, many times, so that's good, right? It doesn't say exactly how many, but it says many, many, so that's good. Does the problem describe a valid simulation design? All right, so let's go ahead and check. So it's a little weird to only generate 1s and 2s, but that's okay. So if you're using a good random number generator, have at it. Enjoy. It's like using dice, right? Dice don't necessarily do 10 digits, but they can work fine depending if you have the right number of outcomes to match your scenario. Since it's only 1s and 2s, then it models 1 out of 2 outcomes or 50%. So we're pretty happy with that, actually. So looking at this, I think it's yes so far. So letting 1 feel addicted and would model, it does model 50%. And as long as we're running it many, many times, we should be fine. So let's check out the other ones. No, it does not describe a valid simulation design. The simulation should be 0 to 5 equals feels addicted and 6 to 9 doesn't feel addicted. You could use digits, but the problem with this setup is 0 to 5 is actually 6 outcomes, or 60%. And the same issue with the next one, 0 to 3 is 4 outcomes, or only 40%. It does not specify how many times to repeat the simulation. It does say to report 100 trials, but it also says many, many times we're running, and that's actually really answering this question. So when you go many, many, many times, that's enough to get you enough data. Presume many, many is a lot. No, it does not describe a valid simulation design. It does not specify that you should ignore repeating numbers. Well, first of all, we don't need to ignore repeating numbers, all right? Because we don't have to worry about sampling issues, like how big are we using up the whole sample. We can assume there are a lot of teens out there, all right? There are plenty of teens, and we're not going to run out of them. So, which is a good thing. Keeps me employed. All right, so we're sticking with choice A on this one. And then last but not least, the partially completed table shows the distribution on the 2016 AP Statistics exam. Suppose we randomly selected a student who took this exam. What is the probability that he or she earned a score of at least 3? So our outcomes are 0, 1, 2, 3, 4, 5, right? First of all, I'm missing a probability up here, right? Right there, I'm missing that puppy. So I need to finish my model, and the model, all probabilities must add up to 1. So I just go 1 minus all those probabilities, and I get 0.144. So we'll put 0.144 in our table right there. Now I'm ready to go. Now, what is the probability that they earned at least a 3? So those are those 3 outcomes. So all I have to do is add those 3 numbers, and I get 0.61, which matches my answer there. So not a tricky question. You just had to make sure that you filled in that missing value and then added up the appropriate values. Personally, big tip, I strongly recommend when you have multiple outcomes like this, show the whole sample space and then highlight what you're interested in so you know what you're dealing with. Hope that helps.